definition of the fluids. The fluid is defined as a substance that deforms continuously when acted on by a shearing stress of any magnitude. More precisely, a solid stress is proportional to strain. See, there is a difference between fluid and solid, right? In the solid, there is a fixed amount of deformation is there, right? That deformation only we are calling what strain. Yes or no?
In a solid?
In a solid, what is the definition of the strain? You might have studied in mechanics of material, right?
No, I didn't take that class.
Okay. Strain means the deformations which are happening, over the original dimensions. That is what we call strain. Yes or no? Now, to explain this particular concept, let me explain you by giving one example. Let's suppose we are having the some rod, right? There is a rod of certain diameter d. Because of the load, there is some deformation will happen. Let's say the length is L, and because of this, some deformation will happen. This deformation I'm calling delta L. So what is the strain? We denote it by epsilon, for example. That is change in length over original length. Getting my point? So that is a strain. The stress is directly proportional to strain by the Hooke's law. But in case of fluid, what is happening? There is no fixed deformation. There is a continuous deformation. If you take a fluid, right? And if you just apply the force P, in the solid, we have the deformation like this. But in fluid, it is continuously deforming. And that is what we call flow. So there, strain rate is important. But in the solid, only strain is important. With respect to time, that means strain rate we talk. D epsilon by dt, like this. Per unit time. We talk about the per unit time. And that is what simply they have mentioned in a solid. Stress is directly proportional to strain. But in case of fluid, it is proportional to the rate of strain or a strain rate. What is that? Shear stress. Getting my point? Shear stress. How to calculate the shear stress? Let's say we have the fluid. Let me give some body here. If I apply the force P, now tell me, and let's say this cross-sectional area is A. What is the shear stress? P over A, right?
What is P?
P is the applied load. Say applied shear load. And what is the A? A is a cross-sectional area. Getting my point?
Yes.
Is it clear?
Yes.
So that is the shear stress. And what is the unit of this shear stress? What is the load unit? Newton, right? Over area is meter square. So we call Newton per meter square, Newton over meter square, or Pascal. Yes or no? Because 1 Pascal is 1 Newton per meter square. Right?
Okay.
Whether this concept is clear?
Huh? Sorry, what?
I'm saying that whether this concept is clear.
Yes, yes.
Okay.
So what will I use this function for?
What?
What will I use this equation for? The shear stress.
We will try to use it in a one concept called Newton's law of viscosity. There, in between the fluids, there is a property called viscosity, because of which it offers the resistance between the fluid layers. And how we are going to calculate? By using that particular law. In that also, this concept will be valid, whatever we are discussing.
Okay.
So have you noted down?
I'll take notes.
Yeah.
When
Recording is
after.
already there, right?
Yeah.
Now moving on to the concept of continuum. That is the next concept which you can see. Again, this concept of continuum is a simple concept where we assume that all the fluid characteristics vary continuously throughout of the fluid, vary continuously throughout the fluid. That is, we treat the fluid as a continuum, and we refer to the very small volume of as a point of in the flow. That means, suppose there is a solid particle, right? In the solid, they are very, very compact, right? They are very close to each other, each and every particle, right?
Mm.
Even you cannot differentiate. But in a fluid, especially in the gas, you can see the difference. There is a
Mm.
gap between the one particle to the other fluid particle. That
Mm.
gap we are neglecting.
Mm.
We think if there is a gap, but there is a no gap. We assume that.
Mm.
Now, what is the benefit of that? The benefit is that suppose there is a bunch of fluid particles at this location, which is having a density rho, which is a function of x, y, z, and t. Density. What is this?
Mm.
Density. Let's say if there is a gap, can we define any property in between the gap, in between the fluid particles which are having the gap? We cannot, right?
Why not?
We see in between the gap, in between the fluid particle, there is a gap. Gap means no matter. No matter means no density, right?
Ah, yeah, true.
Again, for the next fluid particle, we need to define the density, which is again a function of x1, y1, z1, and t1 time. So, like
Mm.
these, can you believe what will be the situation if we are not assuming the fluid to be continuous? That means there is a no gap. This fluid particle is fluid particle, so that we can define a density over a function of x, y, z, and t only. Otherwise, for each and every space, for each and every time, we need to define the density. We need to specify the density. That is a already in the fluid mechanics we have very huge equations, and if we are not assuming concept of continuum to be valid in a flow field, then there is a bunch of equation will be there, and that is very difficult to solve manually
Ah,
or handily. So to
okay.
avoid that,
Continuum.
particular
Sorry.
problematic situation, we basically think if there is a gap but there is no gap, we think like the fluid particles are also continuous like this. There is a no gap,
Mm.
right? So here, that is what they have mentioned. We assume that all the fluid characteristics vary continuously throughout the fluid. That's why we treat fluid as a continuum, continuous, right?
Mm.
And then we have a point, a volume whose length is large as compared to the molecular length scale, but is small compared to the length scale of interest. Fluid
Okay,
properties.
wait, give me 1 minute. Let me check if I understand correctly. So continuum like rule it's basically that we assume there is no gap between the particles, so we can calculate the density in the x, y, z, and t.
Hmm.
Okay. And the particles are like continuous, they are like close together and like continuous, but they're not infinite, right? Continuous is not the same as infinite.
Continuous, I am not getting.
Hmm?
What you're saying?
Like you said they are like continuous.
Continuous. That means there is
Yeah.
no gap, just like a solid, right?
Okay.
Now, but the thing is that, is there any other thing to say the concept of continuum to be valid? For that, we define one number called Knudsen number, right? What is the Knudsen number? Here, if you try to think, lambda over L. That means the molecular mean free path, that is a lambda, and L is what? System characteristic length. You try to imagine a situation. I'm giving you two situations. We have this size and this size room. Let's say we have the fluid particle which is having a gap of lambda. Here we have a gap of this much of lambda we have. Or let me just give you the same room, but here and here we have lambda, and system characteristic length is L. But tell me, in both the case A and B, in which case concept of continuum validity will be much easily applicable?
A.
A, because fluid particle gap is very small already as compared to the system characteristic dimensions, right? So we think
Mm.
like that is a very small gap with respect to the big room. So we think like there is a continuous in between that. There is a no gap. But
Mm.
if the fluid particles are very larger distance, lambda2, and this is very significant. Of course, this is a very significant as compared to the system characteristic length, almost like a same. Now,
Mm.
any third person also can see very clearly that there is a gap. How can you assume that there is no gap? So very difficult to apply for the case B, but very easy to apply for the case A. So for that, we define one number called Knudsen number, and the Knudsen number is saying that the concept of continuum will be valid if Knudsen number is less than 0.01. Right?
What's the name of the number?
Knudsen number. Knudsen number.
It's like less than 0.01, meaning the gap is small.
Yeah, the gap is small.
Ah, okay. Is like, do we need, like when we solve examples, will we need to check for that number to be
We need to
smaller
check,
than?
but that is a numerical point of view. They will not ask. You need to
So it's
just know
not
for the concept.
important in
Yeah,
solving
not
questions.
important. Only concept of continuum is important.
Mm.
Then.
Mm.
So here we have the next concept, dimensions. What are the fundamental dimensions we have? What are the fundamental dimensions we have?
So you're asking me?
Yeah. Fundamental dimensions we have like mass,
What?
length, and time, right?
Mm.
We do have one more temperature, but that is not required. That is required in the
Mm.
heat transfer, right? Heat transfer you have subject, right?
Mm.
Mass means M, length means L, time means capital D, right?
Mm.
So this is what we have the fundamental dimensions, and every formula in the mechanics, every unit we need to specify in the dimensions. Like if I talk about the force is what? Mass into acceleration. What is the mass? Is capital M. What is the acceleration dimensions? What is the meaning of acceleration? Velocity over time, right?
Yeah.
Can you tell me what is the velocity?
M.
Displacement over time, right?
Okay.
Already time is there, right?
Mm.
Now what is the displacement?
The unit, it's M.
Yeah, displacement unit. We have
M.
length.
Right.
And what is the time? T. Again, we have T. So can I write this as LT to the power minus 2? Yes,
Mm.
LT minus 2.
Is there
Like
a
this.
difference between writing it L over T squared?
No. Here it is. How can we write L T square? That can be written as LT minus 2, like this combined format.
Yeah, so there's no, if I write either one is correct, right? There's no difference.
Yeah, there's no difference. But we
And
tend to write like this in a power format, everything, not in a ratio form.
yeah, and like, do they specify in the question like to write it either way, or either is fine?
No, you write only in one way. That is what M LT minus 2, right? In a combined format, what we can write ML T minus 2, which is what they have written for the force.
Okay.
Right? Just note down. Done?
Yeah.
Means have you noted down?
It's recording, so I'm not taking notes. I'll take notes
Okay,
after.
fine. So here we have fluid properties. You can see the fluid properties are, one is the density, right? What is the unit of density? Mass over volume, right? Mass is what? M. Volume is what? L cube. ml minus C, right? Getting my point. And what is the specific volume? The specific volume is reciprocal of density, right? And what is the specific weight? What is the specific weight? Gamma. It's a rho g, right? How we get the rho g? Weight per unit volume. What is the specific weight? The specific weight means weight per unit volume. Getting my point? What is the weight? mg over volume v. What is the mass? Volume into density into g over volume. Then what is the specific weight? Rho g.
Do I need to know how to derive these?
No, I'm just telling you the actually
okay.
how we are. See, actually, I need to tell weight per unit volume, so that I'm explaining this step also. How we are getting rho g. But what is the unit?
Okay.
What should be the unit? G is a gravitational acceleration, right? Again, which is having the same unit as acceleration. So what is the can you just tell me the dimensions? Rho, density. Density already we know that ml minus 3. What is the g? We know that lt minus 2, right? So what you can write? ml minus 2 t minus 2. Getting my point. That is a specific weight dimensions, which is written over here. Right?
Wait, so first
First is the density.
okay, so the first one is like the rho, the density. And the second one is g. And
Yeah.
dimension for g is the same as acceleration, right?
Yes.
Okay. Okay, got it.
What is the next? Specific gravity. So 4 terms are there. First is the density. Second is a specific volume. Third is a specific weight. And fourth is a specific gravity. Getting my point? Getting my point? What is a specific gravity? Density of any object to the density of water, right? Then what should be the dimensions? No dimension, because density unit is also ml minus 3, and the dimensions of density of water again ml minus 3, because it's a density only. They will cancel each other, right? So there is a it is called as dimensionless quantity to specific gravity.
Okay.
So this is all about the dimensions and the property of the fluid. Moving on to the next, forces in the fluid. Basically, we have two forces. One is a body force, because suppose your body weight is there, you are having certain amount of weight which are acting in the downward directions, right? For any person, there is a certain amount of weight, mg. And what is the other force? Other force which is act on a surface of volume of the fluid. Again, I can resolve into two components. One is a normal force and one is a tangential force. Suppose surface force is there like this, so I can resolve like this one, or I can resolve like this, right? So this will be the normal force and this will be the tangential force. Normal force because of pressure. That normal force only we are calling what? The normal stress we are calling pressure, and the tangential force per unit area we denote it by shear stress, right? So basically we have the two forces. One is a shear stress, pressure, and there's a body force, three force.
Okay.
Right. So pressure is a compressive in nature or tensile in nature, like What do you think about that? Now, what is the pressure? Whether it is a normal or tensile. See, whenever we have any fluid element, let me show the example figure which they have given. You can see here, pressure is a consequences of a total flux momentum on a surface element due to the molecular moment of the gas. Here you can see. Okay, let me explain in a very simple language.
Hmm.
There is a fluid element. On this fluid element, on this particular fluid element, the forces that will be acting like a normal force from all the three directions, X, Y, Z. Whatever the forces which are acting over the area, because of that, there is a stress will be generated. That is stress in a fluid we call pressure. So they are always act towards the cross-sectional areas. Getting my point? It will try to decrease the volume or increase the volume of a fluid element. By looking at the scenario, what you're thinking?
Decrease.
Decreases, right?
Mm.
So what is the pressure? Pressure at a point within the fluid is same regardless of the direction we approach the point. We can put the surface through a fluid at any orientation and know the normal stresses on the surface exerted by the fluid. Consequently, the pressure is considered to be a scalar quantity. Why? Why pressure is considered to be a scalar quantity? See, it is from all the directions the pressure is same, right?
Mm.
From all the directions the pressure is same. From all the direction when the pressure is same, then what we can conclude from here? There is no specific directions. When there is no specific direction, that is a scalar quantity, right? Because if I say vector, I will be very specifying in X direction, what is the value of pressure? In Y direction, what is the value of pressure? But here, the pressure in X, Y, Z, all are same. X, Y, Z, that means there is no need to specify the directions. Just say the pressure, that means everybody can understand, okay, in X, Y, Z or random direction, the pressure is same. The pressure value is 10 megapascal, 20 kilopascal or whatever the value. Right. One more concept that is related to the Pascal law. Here in your slide, what they have mentioned, just look at very carefully this particular point. Pressure at a point in a static fluid will remain same in all the directions. As I told you, pressure is a scalar quantity, and that derivation also you can go through, but again not required. Only you need to know pressure at a point in a static fluid will remain same in all the directions. They have taken the what? Px, Py and Pz. Can you see this? What they have taken the element? They have taken Py, Pz, and they have taken what? Ps at any particular angle by taking the wedge shape element, right? Wedge shape element. In that, what they have done, the analysis, here they have not given the proof because it is a very short note, right? You will get to know Ps is equal to Px is equal to what? Py is equal to Pz. That means pressure at in a static fluid will remain same in all the directions. Right? Here in this slide, they have not given the proof because it is a very short notes. Just summary.
Yeah.
The next is absolute or gauge pressure concept. Now, you might be knowing something, so I will be explaining a little bit more. Let's suppose we have the 0 level, absolute 0, right? Now tell me, there is an atmospheric pressure, right? The standard value of atmospheric pressure, what is that? Some 100 kilopascal. Yes or no? The standard value you might be knowing, 100 kilopascal. Or if I specify more, then we tend to write this quantity as this one. 101.325 kilopascal. 101.325 kilopascal. Now, my dear friend, from the absolute 0 level, there is a certain amount of standard atmospheric pressure is there. There is a certain amount of atmospheric pressure is there. Getting my point? That is there from the 0 value. If I say, suppose you are living in certain areas, right? That area, if I say the pressure is at that location, at your location, if I say the pressure value is 200 kilopascal, then what you will understand? That means the total value of the pressure in your location is a 200 kilopascal. You will understand, okay, in my area, the pressure is more than atmospheric pressure. How much extra pressure is there? 100 kilopascal. This is the value. So what is the gauge pressure at your location? 100 kilopascal. Remaining 100 kilopascal is what? Atmospheric pressure only. So from here, what is the total value? That's a 200 kilopascal, right? Getting my point?
Yeah.
What about if I say in your friend location, who are basically living in your city only, but at some different location. If I say the pressure is 30 kilopascal, the net pressure from your location is 30 kilopascal. You will understand, okay, 100 kilopascal, that is already atmospheric pressure is there, but they are saying 30 kilopascal means there is a vacuum pressure of remaining 70 kilopascal, right? That net pressure at that location is 70 kilopascal less than the atmospheric pressure. That is a gauge pressure. So what we can write here, P absolute pressure, that is equal to P ATM plus or minus P gauge pressure. The negative gauge pressure we also call vacuum pressure, right?
What
That is
do
the
you
one
call?
thing. Vacuum pressure.
Vacuum pressure.
Yeah. There is a second thing. Absolute pressure can never be negative. As I told you, it is always from 0, right? 30, 200, they are positive quantity. But the gauge pressure can be negative, can be positive. As I told you in the first, in your location, 200. That means plus 100 kilopascal is the gauge pressure. What about the second case? In your friend location, it's a minus 70 kilopascal. So gauge pressure can be negative, right? Can be negative, but must be greater than minus local atmospheric pressure. That means absolute pressure cannot be negative. It is always positive. But the gauge pressure can be positive, can be negative. Getting my point?
I got the idea, but can you repeat the gauge pressure being positive and negative?
Gauge pressure positive, negative means suppose in your friend location, 30 kilopascal is the absolute pressure, right? From this formula. Atmospheric pressure is 100 kilopascal. So suppose 100 kilopascal. Then what is the value of the gauge pressure?
100 minus 30?
No, 30 minus 100, right?
Yeah.
It's a minus 70 kilopascal. In your location, what is the absolute pressure? 200. What is the atmospheric pressure? 100. What is the gauge pressure? 100, right? 100, right?
Should it, because the absolute cannot be negative, so If
Yeah,
so, if we do
absolute
100
already, you know that it's a 200 kilopascal at your
yeah,
location. I
so
already mentioned that.
yeah, so by the equation is it would have been 100 minus 200, right? But
No,
because it's
200 minus
absolute.
100, right? 200 minus 100, right? If we take this to the left hand side, how it is negative? Positive
Okay,
only.
okay, okay.
So what I want to say, gauge pressure can be positive, can be negative, but absolute pressure should always be positive, right?
Mm, okay. Okay, I got it. Is it important that I knew this diagram to like look at it when I solve like examples?
Yeah, yeah.
Okay.
What? Yeah, I will explain. I will explain through problem.
Mm.
Okay. Moving on to the next concept here, the vapor pressure. The vapor pressure means above the liquid. Suppose you have any container, closed container, and there is a liquid. And there is a vapor, right?
Mm.
On a surface of the liquid, the vapor will try to exert some forces, right?
Mm.
That pressure we call vapor pressure. Getting my point? It is having absolute zero. What is the value? Vapor pressure. Vapor pressure means the pressure which is exerted by the vapor onto the liquid surface, above the liquid surface, right?
Mm.
So here, and we also call the pressure at which the liquid will be start doing what? Boil. The boiling of the liquid will be started taking place at the vapor pressure, right? What is the value of the vapor pressure for the water at 20 degrees centigrade? 2338 Newton per meter square. You don't need to remember. I'm just telling you for the differences,
Mm.
right? Atmospheric pressure we can write. I told you we have the 101.3 kilopascal.
Is it
We
like
all,
a set number for this
yeah,
atmospheric pressure?
it's standard atmospheric pressure that is.
Mm. Okay.
We also call this to be 10.3 meters of water. We also call this to be 760 mm of HEG, right? Yes or no?
Well, let me get it. Can you repeat again?
I'm saying this, there are different units by means of
Mm.
which we can measure the atmospheric pressure. One is a kilopascal, that is 101.325 kilopascal. Second is in terms of 10.3 meter of column, water column. And in terms of mercury, it is 760 mm of Hg.
So it
Kilopascal,
depends on the material.
if you try to
Mm.
convert into kilopascal, so 101.3 into 1000 Pascal. 1 Pascal is 1 Newton meter square, right?
Mm.
So what you can get 1.013 into 10 power 5 Newton per square, right?
Mm. Mm.
Moving on to the next concept, ideal gas law. What is the ideal gas law? PV is equal to MRT. Yes or no? PV is equal to MRT. But if I write M by V, R into T, what is the M by V? Density, right?
Mm.
Density, right?
Yes.
So P is equal to rho RT, where P is what? Sorry, just a minute. Where P is absolute pressure. I told you we have three types of pressure. One is a atmospheric pressure. Second is a gauge pressure. Third is the absolute pressure, right?
Yes.
So what is the P? P is the absolute pressure.
Is it for gases only?
Yes, it is being applied for the gas, that too ideal gas.
So it won't be applied for liquids.
Basically, the liquids at a very which behaves like ideal gas, then we can apply. But it is very rare to apply, for the liquids, right? Now, moving on to the next, and one more thing, T must be in absolute temperature in Kelvin. What is the meaning of, suppose temperature is given as 15 degrees centigrade. You have to convert in Kelvin. 15 plus 273, that is 288 Kelvin. Right? So that is the one thing. Note of the next concept, viscosity. Viscosity. We also call dynamic viscosity. Here. I told you one thing, right? In a solid, suppose if I take two solid objects, one is on the ground. Suppose one is a ground. Ground can be considered a solid object. Where you
What
are
do you
living
mean?
right now, that is a ground, right?
Yes.
So ground can be treated like a solid surface.
Yes.
Can we treat this ground something like this? Let me call this to be a ground. And there is a solid object. Solid object means something like this. Two solid surfaces are there. Getting my point. Two solid surfaces are there. Two solid surfaces are there. When I try to move these two solid surfaces with respect to each other, what will happen? When these two solid surfaces will try to move with respect to each other, they will try to, if there is a friction, so definitely solid surface, this solid object cannot move freely, right? It will feel like some resistance. Same if I take fluid element, one fluid element and second fluid element, it is moving with the velocity v1 and it is also moving with the velocity v2, where v1 is more than v2. What will happen? Again, there is a resisting force will be developed. But in the fluid, we don't call friction force, we call viscous force.
Okay.
Right? And it is happening just because of one property called viscosity, which is denoted by mu. There, which is the important thing, we have the coefficient of friction in the solid surface, but here we have important mu. Right? So viscous fluid sticks or adheres completely to the solid surface. That is called no slip condition. What is the meaning of no slip condition then?
No slip
There's
condition?
a two plate, one plate is fixed. Other plate is moving with the velocity v. Just a minute. Now, if there is a fluid, what will happen? Because of no slip condition, suppose there is a velocity profile like this. The fluid which is coming in contact with the lower plate will have zero velocity, yes or no? The fluid which is there with the velocity zero, the fluid which is being attached or is tracking the lower fluid should have zero velocity, yes or no?
Why?
Because to satisfy the no slip condition. What is the meaning of no slip conditions? No slip means no relative velocity. Are you getting my point?
So there's like no resistance or friction.
No resistance of frictions. No slip means no relative velocity. That means, let's say this, I'm doing analysis of this fluid element and which is contact with the lower plate.
Mm.
The plate is at the rest condition, right? 0.
Mm.
Suppose the fluid particle which is just attaching the lower plate will have some velocity called 1 meter per second. So there is a relative velocity exists or not? If there is a relative velocity, there will be slipping, right? Between that.
Mm.
That should not happen. The fluid particle which is just attaching to the plate should have net velocity 0, net relative velocity 0. For that, the velocity of that fluid particle should also be 0. Similarly, what is the velocity of the fluid particle which is just is striking the top plate which is moving with the velocity v? This should also have the same velocity v, right?
Mm.
So that the gap, the relative velocity is 0. Again, that is called no slip conditions.
Okay, so at the top, at the bottom, there's
Yeah.
okay, velocity 0.
Yes.
Okay.
In between, it can have the difference of velocity. There is no problem.
Only when there's a
Attaching with the solid surfaces, whether it is on the rest or on the moving side, there should also be with the same velocity of what the plates are having, right?
Yes.
Simple fluids for which Newton's law of viscosity. What is the meaning of Newton's law of viscosity? Newton's law of viscosity is that, you can see, just note down, the shear stress will be directly proportional to velocity gradient or rate of strain. What is the meaning of this? The shear stress is directly proportional to velocity gradient. This du by dy will also be equal to what? D epsilon by dt. This law is called as Newton's law of viscosity. In short, I am writing NLV. Please note down NLV. Done. If I remove the proportionality constant from here, if I remove the proportionality constant, I will be adding one proportionality constant, right?
Mm.
That is mu into du by dy. This mu is a proportionality constant. Proportionality constant. Getting my point?
Mm. Yes.
What is this proportionality constant? Mu. And this, what is the mu? It's a viscosity. That means it is a property of the fluid. Getting my point? We also call viscosity. We, in a simple term, we call dynamic viscosity, right?
Mm.
The fluids which follows Newton's law of viscosity, for which the shear stress is directly proportional to velocity gradient or rate of strain, which is that is called as Newtonian fluid. That means the fluids which does not follow Newton's law of viscosity will be called as non-Newtonian fluids. Yes or no?
Okay.
Getting my point?
When
That is
does
the
fluid not follow that rule? Like, what their conditions?
there are certain types of fluid which does not follow. Like you have the starch solution, you have this paints, the coloring we do, right? Houses, that particular fluid that do not follow the Newton's law of viscosity. But if we take common example, air, petrol, mercury, diesel, water, they are the common fluids which follow the Newton's law of viscosity. Right.
Okay.
Second thing, gases. If I increase the temperature, whether viscosity will decrease or increase? Viscosity of the gases will increase by increasing the temperature. See, there are two reasons for having the viscosity in the fluid. What are the two reasons? One is what? Momentum transfer. Second is intermolecular forces. Getting my point? A strong bonding between the fluid particles.
Mm.
In the gases, the momentum transfer is very, very high or predominant phenomena, a dominant phenomena as compared to intermolecular forces.
Mm.
Right?
Mm.
Are you understanding what I'm saying?
Yes, yes.
In a gases, there are basically two things which is responsible, which drives the viscosity. One is intermolecular forces, that is a cohesive force. Second is a momentum transfer. In the gases, momentum transfer is very, very high as compared to the cohesive force because they are very far from each other. If I increase the temperature, every molecule will gain some energy. They will increase their own temperature and they will try to do some momentum transfer very fastly. That's why the viscosity will also increase, right?
Mm.
Because of number of collisions that will increase. In the liquid, if you talk about the liquid, what will happen?
The opposite?
Opposite. Here in the liquid, the cohesive forces or intermolecular forces are strong rather than this or as compared to the momentum transfer, right? These intermolecular forces are very strong as compared to momentum transfer. What will happen?
Mm.
What will happen? When I increase the temperature, this intermolecular forces will become what? Weak.
Mm.
Because see, there is a two particle, liquid particle, they have the bonding. If I increase the temperature, this bonding will be weak, right? They will try to move from each other. So the intermolecular forces will be very, very weak. That's why when I increase the temperature, the liquid viscosity will decrease on increasing the temperature.
Mm.
Getting my point?
Yes. Okay. It's 12 a.m. now. It's like been an hour. So let's like finish for today.
Okay. Should I stop it?
Yes, please.
Okay, yeah.
Smart tutoring, better results. Get started with ExpertBuddy.